colleagues. Welcome to SAMPE's webinar. Today, we're going to learn the latest in composite tank technology for hydrogen storage. My name is Raj Manchanda. I'm the Chief Technology Officer of SAMPE. I'm being assisted by Miss Alexandra Principe in the background. I want to welcome you to this webinar today. We are featuring Matt Villareal. He's the founder and CEO of Infinite Composites. And Matt, I was going to say, is part of a startup, but Infinite Composites has been around for 14 years. So they operate like a startup, but they're certainly a real organization. We're going to have a moderating by Ranji Vaidyanathan. And Ranji is the Villarreal Professor of Materials Science and Engineering at Oklahoma State University. To note, Ranji is also a SAMPE Fellow, and Ranji is also a Fellow of the National Academy of Inventors. What I'd like to do is please go ahead and introduce yourself in the chat. In the chat feature, please enter your name, your organization, your job title, and geographic location. Please, again, in the chat, please self-introduce yourself with your name, your organization, your job title, and your geographic location. We're really pleased that Ranji is dialing in from India, Matt is dialing in from middle of the country, I'm out of New York, and Alex is out of California. So it's a truly global event today. For some other tips, please enter your questions in the Q&A feature. So towards the end, we will start answering questions towards the end of Matt's presentation, but please enter them in the Q&A feature and Ranji will moderate that. Additionally, this webinar will be recorded. Everyone who's registered will receive a link a few weeks after, and you will have a full recording of the webinar after the fact in a few weeks. So just so you know. Other than that, enjoy the webinar. I'm going to pass it over to Ranji to start to self-introduce himself, and Matt with a deeper introduction. Thank you, Ranji.
Thank you, Raj, and welcome, Matt, and thank you, Alexandra. As Raj introduced, I am Ranji Vaidyanathan. I am a faculty member at Oklahoma State University in the Department of School of Material Science and Engineering. And as Raj said, I'm also a SAMPE Fellow and a Fellow of the National Academy of Inventors. I have been involved with SAMPE since the early 2000s, just before 9/11 happened. And since then, it has been my sincere pleasure to be part of SAMPE and to see so many different technologies come through and do that. And this one that Matt is going to present is another one of those that I have been fortunate to be part of. And I would like to introduce Matt. Matt Villareal is an entrepreneur and inventor from Dallas, Texas, who founded Infinite Composites in 2010 while he was attending Oklahoma State University, the School of Entrepreneurship. And the company now located in Tulsa, Oklahoma, it specializes in designing and manufacturing linerless composite pressure vessels. This is the first time anybody had ever tried that, and they did that very successfully for high pressure and cryogenic gas storage in various sectors, including aerospace, defense, and transportation. Matt is the lead inventor on 8 patents in the fields of composite pressure vessels and additive manufacturing. He has co-authored numerous technical publications and presentations on topics such as additive manufacturing and linerless all-composite pressure vessels. And just so you know, there is going to be a paper on hydrogen tanks that we are going to be co-writing for in the SAMPE journal. So look forward to seeing that in print, and we look forward to hearing Matt present his talk. And I will mute myself, and I will also go off video for the time being while he's presenting. Thank you, Matt. Take it away.
Thanks, Ranji. So just one correction. We aren't the first to ever try linerless composite tanks. We were actually inspired by one of another company who had worked on this before, but we may be the first to do it at such high pressures. So appreciate that. But as Ramji said, I'm Matt Villareal, founder and CEO of Infinite Composites. We design, develop, and manufacture the most efficient pressure vessels in the universe for aerospace, transportation, industrial gas applications. Our mission is to make the infinite composite pressure vessel a key enabling technology to accelerate space exploration and sustainable transportation. And just to give you a little background on how we started the company, in 2009, my co-founder and I, while we were still in college at Oklahoma State University, created the world's first compressed natural gas powered Formula race car and drove it 590 continuous miles in a 24-hour endurance race where we set multiple world records. And while we were doing this endurance race, we realized that the all-metal tank that we had in our car, you can see it there in the picture in orange, was really holding us back. It was too heavy, too bulky, and didn't really hold much capacity. So we had to keep refueling the vehicle every couple of laps, and it was really just a drag on our fun at that time. So we started kind of looking around for alternative solutions to the metal tanks and found that composite materials were the key ingredient to making these high pressure gas tanks more practical. So much so that we saw an article in Composites World magazine that was talking about how linerless composite pressure vessels were considered the holy grail of gas storage and could revolutionize space exploration and sustainable transportation. And I was in the School of Entrepreneurship, and I'd been looking for a worthwhile venture to start. And once I saw this article, I said, "This is going to be it. It could impact the world in a big way, and it could be a really fun venture and keep me occupied for quite a long time, which it has." So natural gas has been considered a transition fuel to zero carbon energy, but for transportation specifically, it never saw widespread adoption beyond commercial vehicles, mainly because there's kind of limited government and industry support. Hydrogen, though, as a primary energy source, is still in its infancy, but it's gaining traction from some of the biggest energy producers and consumers across the globe. The governments are investing billions of dollars into the development of the hydrogen economy, and even some of the most heavily polluting industries are really buying in. In 2023, global revenues from hydrogen were valued at $242 billion and expected to grow at a 7.8% compound annual growth rate until 2030. While hydrogen storage only makes up a little less than 1% of this overall market at $1.6 billion, it's seeing exponential growth and driving a significant uptick in the adoption of composite pressure vessels, which are growing at also a tremendous rate of 25.6 compound annual growth rate. Besides, sorry, go to the next slide. So just to talk a little bit about the fabrication approaches to Type 5 tanks, there's really only three primary components that make up this technology. Arguably, the most important is the mandrel shown in orange here. So this is the form that creates the internal geometry of the tank. It has to maintain rigid and precise geometry during the winding process. It has to hold up to curing and also be able to be extracted to leave behind only the composite shell. So there's a few different ways that this can be achieved. Some folks use dissolvable mandrels, so this can be like salts or wax. Some use other water-soluble materials that can be dissolved out with specific solvents. Um, Others use bladders or other types of reusable tools that can be extracted out, but they often have limited useful life, may only be able to be used for a handful of times before they're having to be depreciated. But without the mandrel, it's very challenging to create a linerless composite pressure vessel. And if it doesn't have the right properties, then you can't maintain that optimal geometry and get your geodesic profiles and really make the tank work when you pressurize it. Um, Beyond the mandrel, you have to have the bosses, which is where the valves and manufacturing tooling interface to be able to make the tank, and these can be really challenging. Um, Similar to Type 4 tanks, which are plastic lined, they can use a metal component that's bonded to the carbon fiber shell. Some groups are also using carbon fiber bosses, which solve some of the problems. But when you use metal in these, you have to deal with some uh, differences in coefficients of thermal expansion between the carbon fiber, which has a relatively low thermal expansion, and the metallic material, which can have very high expansion. And where this is challenging is as you're pressurizing and depressurizing these tanks, especially at 5 or 10,000 psi. There's a lot of heat generated through that compression, and so your boss may expand and contract at different rates, and that can cause the disbonding or leakage through that interface. And so this is a really important component of the technology. And if you don't have a truly intimate interface with that, then you can't get high cycle life out of your tanks, which for most hydrogen applications, you're looking at tens of thousands of cycles over the tank's useful life. The third component of a Type 5 tank is obviously the carbon fiber or composite shell. So this handles both the permeation barrier aspects of the tank, but also handles the entirety of the load of the pressure. So in Type 4 tanks, it's similar. In Type 3 tanks, usually you have no more than 10% of the load bearing being taken by the aluminum or metal liner. So in order to achieve this with a linerless all-composite tank, you have to have a very specialized resin system that can withstand the pressures of the pressurization of the operations of the tank. And also you have to be able to mitigate the permeation of the gas coming out. But not only that, you have to be able to mitigate this over a long period of time and over many pressure cycles where microfractures can develop from the stretching and the pressurization up and down on the tank. So that's basically the high level of how composite or linerless Type 5 tanks can be made. That may be a simplistic view of it, but once you really dig into it, it can become very complex, going down to the nanoscale on how you can achieve this with the resins. And there are a variety of processes that can be used to fabricate these tanks, but oftentimes, the most simple approach is the most practical and works, but it's very challenging to achieve that. And it took us about 4 years of developing the technology with some mentors like Ranji and some other folks that were formerly at Marshall Space Flight Center in Huntsville. And so we wouldn't have been able to do this without them. When my team and my co-founder and I originally started the company, we had no idea how to make these tanks, and we basically spent the best part of 3 years traveling back and forth to Huntsville to work with our mentors there, and we made every mistake possible, from the geometries of the domes to how to develop the winding patterns to how we needed to process the mandrels to make them maintain the rigid structure, to how to wash them out and not damage the tank. And so it's a very challenging process to learn, but it's not impossible. So I'm going to talk about a little bit of the different applications that we're working in, and what some of the challenges and testing that we've done on these projects entails. So for terrestrial applications in hydrogen, Infinite Composites is pretty much in every step of the value chain. Some of these products are brand new, and some of them have more heritage. But for power generation, we've recently been working with a partner who develops hydrogen electrolyzers. And so we got some funding from ARPA-E to integrate one of these integrate one of these electrolyzers into the linerless composite pressure vessel, which you can see the cutaway. That was our original mock-up prototype. So the idea here is that with this technology, being able to operate the electrolyzer at high pressure would allow you to do electrochemical compression and generate hydrogen and oxygen at closer to operating pressure. So you can eliminate the need for mechanical compression system or mitigate a lot of it, which makes up about over 40% of the cost of delivered hydrogen. So there was a major challenge here because after we started the project, our customer realized that they were going to need to extract this electrolyzer out of the tank and be able to work on it if there's a failure or a leak or something like that. And so we had to really adapt our design to what you can see on the right, which has a massive opening on the end. It can fit a 17-inch diameter electrolyzer inside. This was a major challenge because optimally your ends, your polar openings on the ends of these tanks have the same geometry. That's how you can get the most stable patterns. This one was a feat that my team said was the hardest tank they've ever made. And we were able to achieve it. This thing hasn't been gone through the actual operational testing yet, but we completed burst testing on this tank. We used a 12-bolt flange on the end, and what we realized was that the load of this flange was such that we could not um, hold the cover, the plug on the end of this flange, because the bolts, even with the highest grade 9 bolts that we could find, 1-inch diameter bolts, we could not achieve over or up to a 10,000 psi burst pressure with the tank, because the bolts would shear off and cause the failure. Luckily, we were able to instrument this tank with strain gauges. We collected that data, extrapolated it, and determined that the upper limit operating pressure of this tank before failure would be around 14,000 psi. And this is just an initial prototype. Another challenge with this tank is everything had to scale up. So we had to find machine shops who could machine these large flanges, which that flange I think is a 19-inch diameter, outer diameter. All the components had to be bigger. We had to really put over 1,000 foot-pounds of torque on each bolt. We had to do some more complex bolt pattern or tightening patterns and processes, and so it required a lot of time, a lot of effort, and a lot of iterations. And not only that, even on the analysis side of how to achieve this and make make the tank work. It took many iterations of finite element analysis and modeling to get this part to work. And so we're very close to delivering our deliverable units to the customer. And these will go to both ARPA-E and NASA for electrolyzer testing. And we're really excited about this project. It's really awesome to be able to be working on this type of product, which to my knowledge is the first of its kind for a linerless composite pressure vessel. So moving on from that, we are also in the distribution of natural gas and bulk transportation. You can see a rendering here of our large scale tanks that we're right now developing the subscale models of through our a contract with the Oklahoma Center for the Advancement of Science and Technology. So for this project, we're developing a 700 liter, 700 bar hydrogen tank that will be certified to ISO 11515 standard. And this should enable the tank to be used and transported in any domain, on the ground, in the water, in the air, and some customers are even looking at this for bulk transportation in space. Now, this is also a big challenge for some of the same reasons as the electrolyzer tank. Everything has to get bigger. The masses of everything are bigger. You have to have significantly more carbon fiber, and the winding process can be very long at roughly 12 hours to do even the subscale tank. So we had to really advance our resin system to be able to handle those long winding times, and we had to develop new polar Boss technology to accommodate for the large mass and the large heat input from the pressurization up to 10,000 psi. So these are quite challenging. We also had to implement a 10,000 psi, or I guess 12,000 psi test system for both hydrostatic testing, where we upgraded to a 50,000 psi capability, and then for some pneumatic leak testing up to 12,000 psi. So this took a lot of work on from our testing team to get this capability in house. It's something that we've wanted for a while, but haven't had forcing function to make us do it. But it will allow us to test every single one of these up to operating pressure, slightly above operating pressure, with mostly helium, because the hydrogen can be a little bit challenging to do in a small facility. But we'll be able to do that and confirm their leak tightness through that process. And just for some context, and we've previously tried to outsource this type of testing. We've been quoted anywhere from $30,000 to $50,000 per test to do this leak test, and so you really want to do it on every part so that you make sure that you're not going out into the field and then developing leakage after the fact. Just going down a little bit on the lower picture there, that's actually a CNG fueling station. It's a mobile application that can be picked up and dropped off anywhere. We're also working with some partners to develop this for hydrogen using the same technology as our bulk transport tanks. And the beauty of this is it will make the development of hydrogen infrastructure can be more ubiquitous, because it can be done anywhere that you have a water supply, electric supply, and a way to turn the water into hydrogen, or even from a hydrogen pipeline. So that's a project that I think can be really impactful to the hydrogen economy and solve one of the big critical problems. moving on to our tanks that we're developing for transportation applications on the ground. So we're right now getting close to the end of a contract with the U.S. Army to develop conformal hydrogen tanks for 10,000 psi operation. You can see one of the cylindrical tanks there. That holds about 5 kilograms of hydrogen. That's kind of a baseline tank that could go into a larger scale vehicle, a truck, like a pickup truck, or even in some cases on a semi or a bus. For the application that we're working on for the Army, this is intended for an M Razor, which you can see that's the picture of the vehicle there. And so it's a much more compact form factor. There's not a lot of wasted space on this thing. And so we developed this conical tank that can fit into some of the tight spaces on that vehicle. And we've gone through quite a bit of testing on this. We've done about 7 burst tests on these tanks, having all but our first attempt go above 24,000 psi. We did a number of pressure cycles on these. I think initial shot was 750 pressure cycles up to 12,000 psi on this vessel, and still maintained a 24,000 psi burst pressure, which exceeds the requirements for the HGV2 standard. The biggest challenge here is building up this much carbon fiber on such a small tank. I believe this one's roughly 6 inches in diameter on the largest end, and about 20 and change inches long. It it builds up a very thick composite. It's getting very close to a thick wall composite, and so you're having to deal with the differences in stress on the inside and the outside of the tank, which made it a little bit less predictable than we had hoped. But we were able to get these tests done. We instrumented strain gauges on almost every tank, so we collected a lot of data, and we were eventually able to correlate our finite element models with the as-built parts. And the next steps in this test program, we're going to be doing a filling test to determine what the maximum filling rate is with hydrogen on these tanks. One of the challenges with linerless composite tanks versus, for instance, your metal line tanks is you do have that large buildup of heat during pressurization on the ends, and so that can cause premature cutoff of your filling and incomplete fills. So we've incorporated some technology into our resins that enable it to distribute that thermal buildup over the entire composite of the tank. So we will be doing that here in early January. And then beyond that, we're doing a composite flaw test where we're going to induce a flaw or 2 flaws into this tank, and we have to complete another 750 pressure cycles with the tank to 12,000 over 12,000 psi. We're pretty confident that we will be able to achieve this and maintain a burst pressure of at least 80% of the requirement, which I believe is 22,000 and change psi. And then the final test for this this initial contract will be a ballistics test. So we're going to take this tank out to a tow missile range that's here in Oklahoma, and pressurize the tank to 10,000 psi with hydrogen, and penetrate it with a armor-piercing 7.62 by 39 round from an AK-47. And the challenge here, which I think that we'll be able to achieve, I have high level of confidence, is that the tank can't catastrophically rupture. So the bullet has to pass through the tank, penetrating it, and leaving only a hole or 2 holes, and allowing the gas to evacuate the tank through those holes without a catastrophic rupture. So these tanks or these tests, especially when you're going to the 10,000 psi range, or even higher with gas can pose some serious challenges, not only with uh, getting the equipment and building the test systems, but also with the safety. We recently did some testing with the Army and NASA at the Redstone Arsenal, some of our tanks where they were uh, fixed with shape charge explosives and pressurized and blown up, and the fragmentation was measured, and that requires a lot of safety precautions. And the boss on one of the tanks that was done during the test was calculated to have shot up straight in the air over 1.6 miles. And it took about 25 or 26 seconds to finally come down. So you have to have a very large area to conduct this test. You got to have a very safe bunker to do this, just in case something goes wrong. And when you're using hydrogen as the test media, there's always a chance of ignition and rupture. So you have to take a lot of safety precautions, which can make the complexity of these tests quite challenging. The buildup of the tests quite expensive, and the operation of the tests quite dangerous. So we've been working with partners at the Army and other federal agencies to make sure that we're doing our diligence and making sure this is a safe test. But it's going to be really fun, really exciting. Either way, if it passes, it's going to be very exciting. If it fails, it's going to be a very exciting failure. So uh, pretty confident though that the technology is going to survive. So moving on to some of the projects that we've worked on in hydrogen aviation. So there's been a number of projects, both manned and unmanned, that our tanks have flown on, including a hypersonic aircraft that was powered by hydrogen, some UAVs that have used hydrogen fuel cells for defense applications. And then we're working with a partner who is doing some perpetual flight applications to basically replace their pilot with a hydrogen fuel cell system to enable their flight time to exceed 24 hours. Um, there's a lot of testing that goes on in these, and in the air. Your mass efficiency is far more important than on the ground, especially for these applications where it's really critical that you can maintain flight for as long as possible. For instance, in the Department of Defense, you want to be able to extend your mission range. You want to be able to add more payload to your vehicle, and all those things are trade-offs that you have to make when you have a heavy tank, and when you're going up to 5,000, 10,000 psi with a metal tank, that can be prohibitive, and really limit the capabilities of the vehicle. And then on the perpetual flight, this is intended to replace like a satellite orbiting the Earth. And so being able to maintain that flight for an indefinite duration would make this technology competitive with satellites at a fraction of the cost. So it's incredibly important there on the unmanned applications. And the testing protocols for the unmanned are a little bit more forgiving. We use the AIAA SO81 standard for testing these tanks, which only requires a 1.5 times safety factor for the unmanned application. So you can get really high mass efficiency out of these vessels. And the testing programs are less. There are less tests in the programs versus the ground-based applications. So, for example, in the ground-based applications, you may see 16 to 20 individual destructive tests that you have to go through to achieve the certification, which can be, prohibitively costly for the manufacturer, but these things are, in close proximity to a lot of risky items. When they're on the ground or in a war zone, anything can happen, and so you really have to have that higher safety factor, and you gotta plan for everything. With the unmanned vehicles, unless they're in a war zone, there's much less risk of you know random mechanic dropping a wrench on it or a car crashing into it. And so the test programs are a bit more forgiving, but still quite rigorous. So we've developed a number of hydrogen tanks for these unmanned aircraft. Um, in the ranges of 2 liters to 136 liters to 200 liters, and anywhere in the middle. Um, and these have gained some flight heritage. And we're looking at some implementing some of the conformal tanks on these vehicles as well, which is really exciting, um, but also challenging. So on the manned aircraft side, some of the same tank geometries that we've used for the unmanned vehicles, and for some of our space applications, we've adapted to manned aircraft programs. Um, the um, the testing regimens are less developed for these hydrogen applications, but they're getting more and more developed and more standardized. But we've developed some uh, 2 vessels that have can hold 5 kilograms of hydrogen for these applications, and just got word that so one of them is flown on a more fixed wing aircraft, and we just got word this past week that our other design got flight heritage on a military rotocraft with a major defense prime. So we're really excited about that. These tanks have passed um, burst pressure cycle testing to 1,000 cycles, and crash worthiness testing through the DO 160G standard. And there's quite a bit more to be done to put these into full operation. Right now, they're getting used in mostly experimental aircraft, but as the standards progress, and the vehicle technologies progress and become more developed and more ready for commercial uses, we see the testing programs becoming far more rigorous and increasing the number of tests and the number of risks that are being mitigated by these tests. So the final area where we are working on some hydrogen programs is the final frontier of space. So we've developed a number of products that are being integrated into various um, vehicles and spacecraft, most of which are headed towards the moon, including lunar landers and some infrastructure applications. The testing requirements from the standards are mostly the same for the space applications versus the aviation applications, but the um, the customer requirements and the requirements from the range, from the launch ranges, can be significantly complicated and challenging. So, when you're sending something to the moon, it's a long journey. You can't really do anything once the vehicle's launched to mitigate challenges and mitigate failures. Um, and so you really have to cover all your bases. And also, the cost of sending a kilogram of payload to the moon is $1.6 million or around that number. So the impetus for the most mass efficient tank possible is really valuable. And so this creates some unique challenges because you have to make the tank incredibly robust as far as being able to handle damage and handle the rigors of the space environment and the lunar environment, everything from like micrometeoroids to massive changes in the temperature on the surface of the moon, but also you have to make this as light as possible, and so the the testing can be incredibly challenging. It can take a long time. Many of our programs are going into their final years after 2 and 3 years of development, and getting ready to be integrated into these lunar vehicles for launch in mid to late 2025 and early 2026. Um, and then in addition, as I mentioned earlier, the infrastructure application. So in space, you have to have a way to get energy. You have to have a way to get back off of the moon and get back into orbit or go to Mars. And one of the most efficient and most promising methods is for hydrogen. So the electrolyzer technology I mentioned before is intended to be used for through the extraction of water ice and converting that water into hydrogen and oxygen, and that being used both in some life support applications, but also to power these launch vehicles and other vehicles like this Toyota here to be able to have a consistent supply of fuel and be able to accomplish their missions and really to establish a permanent civilization on the moon. Um, so the testing programs, as I mentioned, they're quite rigorous, but it's hard to compare them to the ones that are on the ground because you have to have that low mass, and so um, the the challenges there are similar but different. Um, and that's really what I have for the presentation. We're working on projects in every domain for hydrogen and other high pressure and cryogenic gases. And if you're interested in seeing if we can provide a solution for you, feel free to reach out to me at Infinite Composites, or you can go to infinitecomposites.com where we have an RFP form so you can fill out kind of what your technical specifications are, and myself or one of my team members can follow up. Thank you.
Thank you, Matt. Um, Alexandra, can I start reading out the questions that have come from the audience?
Yes, you may.
Okay, so there are quite a few questions, so let me read them in the order we got them. So Matt, here we go. The first
Sure.
question is your dome shape proprietary or a standard design?
So the dome shape is a very specific geometry, which changes depending on the diameter of the tank. It can also change from the pressure rating of the tank, because you're trying to maintain the geodesic profile or the geodesic path of the fibers to optimize their load bearing efficiency. We use a base dome geometry that is common, but we also optimize that for our process. So it is somewhat proprietary, but it is a derivative of a more standard dome geometry. But it's not hemispherical, and that's one of the challenges, or one of the big mistakes we made early on, was that we didn't realize that there was a big difference between metal tank having a hemispherical domed end and how you have to have a different shape for an all-composite tank or even a metal line composite tank.
Okay, so the next, there are a couple of questions, Matt. The first question is, if your winding times on your large-scale tanks are over 12 hours, have you explored the use of pre-preg winding materials to mitigate the resin from kicking over during the wind?
Yeah, so we have considered pre-preg materials. We've tried some pre-pregs in the past. For us, we like the flexibility of using the wet winding system because we do use proprietary resin systems that are not. It's not like a component A and a component B from a specific vendor. So we have a special sauce that we use in that application. And we like to be able to modify that for different use cases, different material compatibilities, and really optimize it for our manufacturing process. The other challenge with the pre-preg is oftentimes they're quite a bit more costly than than wet winding, and so we really want to make our product is very premium. The end goal is to make this technology ubiquitous, and to do that, you have to have a cost-effective solution. And so I think that for keeping the cost down, we're probably going to continue focusing on wet winding systems where we can control every component and we can control the costs as well, and not throw away not waste material that may it may partially cure or it may go beyond its out time during the process.
Jared also suggests this. AIAA S81 is meant for type 3. And have you looked at AIAA G082, which is for type 4? And you might want to talk to Tommy Yoder at NASA White Sands on certifying type 5 for aerospace applications.
Yeah, so I am on the AIAA Aerospace Pressure Vessel Steering Committee. I'm aware of the guide SO82, and we do have some customers who are more recently looking for us to certify to those to an SO82 standard. It's not really a standard, but it's a guide. But for SO81 and SO81B, we basically do a tailored version of that allows us to complete the testing and not do some of the tests that are more specific to the metal line tanks. We are also in communication with Tommy Yoder and the guys at White Sands, and so we are aware of that, and we're working towards some certifications through that standard or through that guide.
What is the storage efficiency, weight of hydrogen over weight of the tank that you are getting on your 10,000 PSI tanks?
The 10,000 PSI tanks are not quite as efficient. They're probably on the order of 7 or 8%. On some of our 5,000 PSI tanks, we're achieving up to 12 and 14%. Those are being designed to more aerospace standards, so there is a slightly lower safety factor on those at a 2-time safety factor versus the automotive requirement is 2.25. But on those, mostly above 10. But those have had far more development on them, and we've been able to optimize them quite a bit more than the 10,000 PSI tanks are still very early development, and none of them are ready for prime time yet. So as we get through our proof of concept testing and achieve the minimum viable product, we'll spend a lot more time on optimizing the winding pattern and reducing the weight. Right now, the goal is to get the tanks to a functional state to where we can prove that they can operate at that high pressure, and then we can start optimizing the geometries and the winding patterns to make them far more efficient.
What are the difficulties, if any, that you faced during carbon fiber impregnation with the resin, and how did you overcome that?
Maintaining a consistent fiber volume fraction can be challenging, especially when you have resins that are loaded with additives that change the viscosity of them. So for one, we use a electronically controlled doctor blade, which gives you a precise resin content that you can, adjust and kind of on the fly while you're winding. If things are getting a little more wet or a little more dry, you can make some micro adjustments. And we do some very crude tests of the resin content during the winding process to confirm that we're in the sweet spot of roughly between 60 and 65% fiber volume fraction. The other thing that helps a lot with maintaining the fiber impregnation is to have a water bath on your resin bath, or water circulator on your resin bath, so you can warm up that resin to a precise temperature, get the optimal viscosity to fully impregnate the fibers and get full wet out.
How does the hydrogen leak rate compare with Type 4 tanks?
We've been able to achieve basically parity with Type 4 tanks with our vessels. So they believe the standard in the NGV or HGV2 standard is I'm trying to think, it's like 1.1 times 10 to the negative 4 standard cubic centimeters per second. We've achieved 2.5 times 10 to the negative 6 standard cubic centimeters per second on some of our tanks. As you go bigger, that was a small tank. On some of the bigger tanks, that goes up, but we've been able to achieve basically parity with Type 4 tanks.
Thoughts on challenges of availability of high-grade carbon fiber as the use cases and production of pressure vessels increases, and any insights on using healable, repairable material like thermoplastic from a recycling viewpoint and extending life certification by repairing?
As far as the carbon fiber supply goes, it's way more challenging in the aerospace and defense applications versus your more commercial ground-based applications. In the aerospace and defense, the customer is really pushing for the most optimal fiber. So your Toray T1100 or IM10s, those are a little bit more challenging to get a hold of. You have to certify that you're not using them sometimes for weapons of mass destruction and things like that. But there's a very limited supply of those. On the more industrial grade fibers, we haven't really had much challenges with the supply chain. But I do know the supply chain is expanding, and there's new lines coming on in the U.S. Fairly regularly. So as the demand goes up, there's more of an impetus for suppliers to create more supply to keep the cost down. And we're interested in using recyclable stuff, but I don't really see that repairing the high pressure tanks is viable because it's hard to predict, and you don't want to really take the risk of repairing this after the composite has been damaged. It is a continuous fiber reinforcement, so breaks in specific locations can just create a bit too much risk.
Is there any requirement for fire resistance of pressure vessels? And if yes, what is the most commonly used approach?
Was that fire systems? Can you repeat that, Ranji?
Is there any requirement for fire resistance?
Yeah, so there's bonfire tests that have to be completed on the tanks, similar to the natural gas vehicle tank. So you pressurize the tank with a fluid, and you put it over a bonfire. The main goal, so you can pass the test by just not rupturing with over a certain period of time. But the most practical way for a lot of applications, especially ground-based, is to have thermal pressure relief devices. So this, somewhat dependent on the size of the tank, whether you have just one pressure relief device or you have to have multiple remote PRDs. But that's really the way. You can do fire resistant additive like clays and other things in your resin system to outlast the fire. But those can just increase the complexity of your resin and make it harder to predict. But they are possible.
Okay, in the unmanned fixed wing burst pressure test, how much was the burst pressure, and cyclic tests were mentioned? Were those thermomechanical cycles?
The burst tests, let's see, for the 5,000, they would have exceeded 10,000 PSI. The cycles were not thermal cycles. It wasn't required for the customer or through the standard. They were, I believe, the minimum for the AIAA standards is 500. We did 750, I think, on one tank, and we did 1,000 on another tank, but they were not thermal cycles.
What technologies exist for the integration of the boss elements, and how do you approach this during winding around the mandrel?
Yeah, I'm not really going to comment too much on that. I mean, a lot of it comes down to the preparation of the metal and the getting an intimate bond with the carbon fiber. Some companies in the Type 4 range, they do mechanical interlocking on their tanks, but this is the big challenge. This is part of what makes our tank special is we're able to maintain that over 20,000 or more cycles. So I can't talk too much about that one.
Okay. I think, Matt, that's all the questions that we have, but I think that's quite a lot. So thank you for answering all those questions, and thank you for ensuring that we kept within the 1.5 hours time slot.
No problem. Appreciate you guys as well. Thanks for everyone who attended the webinar.
Thank you, everyone. Hope to see you back on January 15th, I believe. Thank you, everybody.
Thanks all.
Thank you. Thanks, Matt. Thank you, Raj.
Yep. Thanks, Ranji.
Thanks,
Thanks,
Alexander.
Raj. Thanks, Alex.
Alex, yeah.